So I also record every lecture to the best of my ability unless there's a technical snafu, and I post these on YouTube. And so you probably want to subscribe to my YouTube channel so you can get, there's like nothing good going on there, I trust me, it's just this. There's nothing fun going on. There's like, if you miss class, that's there. And I think I've got the link to it. Maybe I'll send out the first one so everybody has that. But your assignment 0 is log into WebWork and try something. Because it won't do anything unless you try something. Just anything. Don't even get it right. Just like guess. The way I hook this up is you have infinite chances. This is like your lifeline to getting an A in this class. You have infinite chances to get 100% on every assignment within a fixed time period. Okay, so keep trying that. And what I'm hoping is that maybe even by Wednesday you'll try something beyond just like entering nonsense, and then you'll have questions for me on Wednesday about this assignment, and we'll talk about whatever questions you have. So homework 0, and I'll put a grade in the book. It'll be 10 points. Sure, whatever. Do that, and then I'll check Wednesday before I come in. So please do that. And let me know if you have any problems. Again, here's my email address. Cool. So, next business. Oh, thank you for the sheet here. This is great. All right, in the content area, let's see, what do we have here? Oh, I've got all sorts of stuff. First off, a gift. I have, through years of discrimination and trial and error, come up with the perfect calc reference sheet. This is from the inside cover of one of my favorite calc books. It's like the calc book I learned from, and that's not just why it's my favorite. You could use this in every class. This thing has all sorts of formulas. Look at all that. That's not even calculus yet, right? Just all sorts of beautiful graphs you should know. And then the calc starts here. Great differentiation rules. Look, they even have this little handy cut line if you want to print it out. And I don't know what you do with it. I don't know why you'd cut that, but I guess you would. And then integral tables that will become near and dear to you this semester. So that's the first thing I want to point out. Second thing I want to point out is our text. And if you're at Regis, you probably used active calculus. You will continue to use active calculus. And what I find is most people don't read textbooks, almost ever. Sometimes, yeah, right? Yeah, I mean, come on, you're probably not going to. But it's there for you, so that we can say we have a textbook, so done. Here's our here's my YouTube channel, and it's not spelled quite right, but you get the point. So you can go here, and I highly recommend just going there and subscribing so you get notifications when the class videos are posted. Our syllabus, let's just take a look at what is expected of you this semester. My office hours are right after this class on Mondays and Wednesdays. And then Friday after this class, preferably by appointment, but I'll totally like hang out with you if you want, absolutely. On Fridays, we only meet for like 50 minutes. All right, so we meet 3 times a week, 75 minutes, Monday, Wednesday, and then 50 minutes on Fridays in the same room. So I can hang out with you after class on Fridays anytime you want. And then my Thursday hours are Zoom. And I'll like have the Zoom camera on. I'll be sitting at my office at home waiting for someone to show up. So I'm there for you. I'll get that Zoom link to you pronto. It's not there right now. We can also set up Zoom appointments. Yes?
What time is our class on Friday?
It is. It starts at the same time, 11.
Okay.
Yes, that's a great question. So 11 to 11:50 on Fridays. Yeah. Okay, so let's see here. Required supplements, web work, free. Everything's free. That's the way it should be. Oh, make sure you're not getting screwed by the bookstore. And you probably already have. You are by default screwed by the bookstore, right? They opt you into this ridiculous system, and then that overcharges you for things you don't even need. You don't need a book for this class, it's all free. So I would opt out of that. Make sure to opt out of that. That's your money and they want it. Don't give it to them. Campus bookstores are criminals. On tape, but we got it on video right there. Calculators, oh no, cell phones, please don't do that. And if you got a laptop, please be using it for class. That's cool. I appreciate laptop use in class, but don't be like watching videos and shit. Calculators, no, unless we like specifically use them that day. No calculators will be used. You will become mighty and powerful. Powerful like that. Powerful up here. Attendance, you know, you're in college, do what you want. You miss though, that's on you. The videos will be there, but like if you miss a test or you miss a quiz, you really need a good excuse because everything's announced so far in advance that if you miss, a lot of times people are missing intentionally, things like that. So I don't want to presume anything about you, but that's kind of my policy. There's like no makeups unless you have a good excuse. Late work. So let's actually talk about that. These web works that are up, like we will negotiate the end dates. So like this current one, there's a web work one up and it's stuff we're gonna talk about today. That is due at the end of the day next Monday. Throughout this week, we'll take a look at that and we'll say like, hey, are you guys doing okay on that? Do we need to extend that deadline? And if you want, if you're like, I need another day, just tell me. We'll make it another day. But what I won't do is at the end of the semester, like open up WebWorks for you to go back and do. I want you to like keep up because that's gonna be best for you. And then, you know, it also like pays off people who kept up those things. We have 3 exams, 15% apiece, and that includes the final. So the final is just a regular exam. It is not comprehensive. It doesn't need to be, because it'll build off everything we've done. And there's my grade scale, there's all sorts of the blah, 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 blah. Oh my God, so much crap I have to put in there. Go, you can read it if you choose. And if you don't, that's cool too. Let's see, is there anything else we need to talk about here? Nope, that's it, good. Let's do calculus. Good. I think this thing is not behaving and I need to shut it down, man. So, how many folks had calc with Dr. Gravel? Cool, lots of you. Okay, some of you had calc with me. A couple of you had calc with me. So I know what you know. We talked this morning, so he told me where you guys left off, and so we're going to assume, we're just going to work from there. I usually get a little further in my Calc 1 classes up through substitution. He didn't quite get there, that's okay, so we're going to build off that knowledge that you already have, but we're going to review a little too. I guess I should ask, are there any questions you all have? So I've been rolling. We're all good? Cool. Awesome. Need a sip of tea. Alrighty. So this whole class, let me tell you a story. Here's a quick meta story. Calc 1 is about this. What's that the definition of? Derivative. Calc 1's about derivatives, right? So you say f prime of x is that limit. Calc 1 is about subtracting and dividing. That's what this definition has in it. Calc 2 is about adding and multiplying, for real. Like the fanciest freaking addition and multiplication available. Thanks to Isaac Newton and Leibniz and a bunch of other people. The ideas we're going to talk about today are ancient. This isn't just like calculus is this weird archaic thing that's alien to humanity. Calculus is like part of who we are. It's part of the way we interact with the world. It's part of our experiences, just being a human. The first calculus was done in the first civilization. So you go back to ancient Sumer, Babylon. Those folks, you know, on the banks of the Tigris, were doing calculus. They didn't have the symbols. They didn't have, you know, derivative symbols and integral symbols and all that stuff. But they did have the ideas that we still use today, and we've refined and really, you know, codified and just expanded upon and made quite beautiful. But this thing of calculus is like, this is you. This is an alien. This is like, and actually I'd say it's like maybe one of the greatest achievements of humanity. I'm sure everybody says that in their classes, like every day today. You know, you go to music class. This is the greatest thing. History is the greatest thing. Whatever. The Babylonians, before I write this, the Babylonians computed the position of Jupiter in the sky using integration. So like, you know, we think of these ancient people as like, oh, you know, they're ancient people, they were very primitive and stuff. No, fuck no. These people were geniuses. Like more of a genius than I'll ever be. Those folks. So you like when you think, you know, they were like scared of the sun and stuff, the eclipses, and they like trembled in horror at eclipses and things like that. No, they saw Jupiter moving across the sky, and you know, there's this like retrograde motion and stuff that planets do. Sometimes they slip back across the sky as you watch their motion. And they used calculus to predict where Jupiter would be in the sky at different times of the year. And they used the stuff we're going to talk about in just 1 minute here. They also used calculus to compute the volume of boats and casks to hold things. Like this stuff's crazy. And so it's been around for thousands and thousands of years. You can do it too. It's part of you. It's in your brain, it's in your heart. It's in your blood. So let's just start talking about the thing that the first part of this class is about. So this is like the first 2/3 of our class, integration. And then the last third is very different, but it's still just adding stuff up. And it's really cool. Then it gets really weird. And along the way, you're gonna see some really crazy things, because I love crazy things that are counterintuitive. So let's just start off with this idea of integration. By a simple example, and I know that Dr. Gravel, how did he say his last name? Gravel, thank you. Dr. Gravel used this example, and I think it's a really great example. You're in your car. We talked about this. I was going to do a totally different one until he told me this example. I thought, that's a good one. Let's go with that. You're in your car, you're driving, and you look down at the speedometer, and you notice you're going, let's say you're on a highway, you're cruising at 70 miles per hour. You're taking a long trip, yeah? Nice long trip. So you're driving down I-70, just cruising at 70. That's, I guess 75 is the speed limit, right? So this isn't crazy. This is a good speed, it's a good safe speed to travel. You're driving, you look down, I'm going 70. And you like listen to your tunes, spacing out, driving somehow you managed to keep driving quite well. And then, 15 minutes later, so this is, let's see, this is time 0, this is my time axis. 15 minutes later, so this is in minutes as well, you look down and you go, I wonder, man, I've been totally lost in thought. Shit, how fast am I traveling? You're like going 85. 15. Whoa, better, well, let's see. No, there's no fuzz around. This is all cool. It's like pretty abandoned. I'm just gonna keep going. And then you come into a town another 15 minutes later. So at 30 minutes, you pull into, I don't know, some small mountain town, and you really you lay on the brakes. You come down to 50. This is pretty bad. that scale here, by the way. Down to 50, so let's see, here we were at 70, we were at 50. And then you kind of cruise. The town is a big, long town, and you're just like, you like that speed, so you can, let's see, at 45, you're still going 50. And then you pass out of the town, and you floor it again, not even sure how fast, and 15 minutes later, so an hour has passed, you're back at 70 miles per hour. So in that hour, how far did you travel? So this is a question. This is the question Sumerians could answer quite well. So here's our plan. There's a couple of plans that we can take here. What's our attack? Well, I only have these data points, and for some reason, you're like a nerd, right? Everybody in here is a nerd, right? Like, we're science people, we're like math people, we like numbers. I hope you like numbers. I don't know what you're doing if you don't like numbers. This is gonna be a long friggin' road if you don't like data and numbers of some kind. So you look at this little chart you made, you pull over to the side of the road and you're like, shit, how far did I travel? I didn't really even notice the odometer. So the best you could do is estimate. And you could say, let's see, I was going 70 here, so I don't know how I increased from 70 to 85. I don't know what the shape of that acceleration was. So the best I could probably do is say, I'm going like that. So I stayed 70 for those 15 minutes. How far did I travel? Let's put this into hours. Since this is miles per hour, let's fix this unit into hours. So this was 15 minutes, so that's a quarter of an hour. This was half an hour. This was 3/4 of an hour, and this was a full hour. Is this making sense? Yeah, we good? Any questions on what's happening? Okay, cool. So for this first quarter of an hour, I was traveling 70 miles per hour. How far did I go? So what's my distance here?
(70/4).
Yeah, a quarter of 70, right? You're going 70 miles an hour. That means in 1 hour, you travel 70 miles. So if you're doing that constantly for a quarter of an hour, you've traveled 70 times 0.25 miles. What about here? Okay, so then we come to this next one. We noted we were at 85. And I traveled 85. So I'll put the 70, there's 85. I traveled 85 for a quarter of an hour. Somebody besides Isaac, tell me, how far did I travel? Just the computation, they don't have, yes?
85/4, and then you add it to the previous one.
Beautiful, beautiful, love that. So in this little block here, we went 85, what's your name?
Abraham.
Abraham, hi Abraham, thank you. So 85 times 0.25, and then we'll figure that, we don't even, who gives a shit what the actual numbers are, right? Like this, we could do this if we wanted to, this is easy. And then as Abraham suggested, I would add these together to get my estimate of how far I've gone. So I'm gonna add these to get the total distance so far. Check it out, I'm multiplying and adding, right? Yeah. And so then the next one, next data point we were at 50, and we went 50 for another 15 minutes. So I think we got the rhythm here, right? It's gonna be 50 times a quarter of an hour. That's how far I went. So plus 50, so my handwriting's a little janky, sorry about that. And then this last one, let's see. Where are we going? Over here, right? That's, no, right there. We're using the left side. So the last estimate, even though I was at 85 or 70 at that last data point, the way I started was I was using my initial speed, my initial velocity at each of those intervals. So I'm gonna keep consistent starting speed at that interval. So the starting speed here was still 50. And so in this last one, I've got an estimate. And that estimate is going to be another 50 times 0.25, because I don't really know what happened in here. I don't know how I got from 50 to 70. I was driving. I don't know what's happening while I'm driving. So this is an estimate of the total distance. Let's actually do it. What the hell, right? Like, why not? So let's see. So one way to do this is notice that it's 70 plus 85 plus 50 plus 50, and you can factor out the quarter. And so what do we got here? 170, 255, and a quarter of that. So this is 255 times 0.25, and I don't know, 60 something. Can somebody?
63.75.
Cool. So we got an estimate. Is that the only estimate I could have made? What? So yes.
You could have done trapezoids if you wanted to be more specific.
Oh, dude. Are you trying to woo me? That is like gets my heart all warmed up. Yeah, we could have done something way fancier. Holy shit, we're not going to do that today. But let me just, we'll come to that in a little bit. But, and what was your
Jeremy.
Jeremy. So Jeremy was suggesting I could have done something a little fancier, and that would be, well, those guys are going to be okay. But to estimate these things here. Now, the problem with that is we need a little bit more sophisticated idea of, because like right here, Jeremy's going ahead into the idea that this area underneath these things is the thing that I was computing. It's not as obvious as it is when we have these nice flat tops though. So I do want to keep those nice flat tops, but Jeremy, that's totally brilliant and a much better plan. What's another way with flat tops that I could have done? Yes?
You could have instead done it from the right side instead of the left.
Totally, yeah. So another way, so these are all totally correct. That's the one I was thinking of in my head. So check this out. We could have also done this a different way. So we had these 1, 2. So our first estimate, we noted it was 70, but we could have started with that second data point. So remember this was 85 right here. And this was 70 here. And we could have said, okay, well at the end of that first quarter of an hour, I was going 85, so who knows? I'm just gonna say I was going 85 the whole time. And what's nice about these rectangles is that you have a constant distance. So I can literally say, you know, distance equals velocity times time. And we could go across and do this all. Let's actually be consistent. So then the next one was 50. So here we had a 50. And then here we had a 50, and then here we had, what was that last one, 70? Thank you. So over here, 70, I didn't need that dude at all. So I could have used my end speed at each of those times to get an estimate. So this is using initial speed, initial velocity, and this is using end velocity. So I kind of just like the nerd in me wants to do this. So let's see, so this was 85, this was 50, 50, and this was 70. So each of these is a quarter. And notice that this is just the area of the blocks. So you can just like abstract this. And so we're just finding the area of each one of these. So this estimate is going to be 85 times a quarter plus 50 times a quarter. Notice that center computation actually occurs in both of these. Plus 50 times a quarter, and then finally plus 70 times a quarter. And I bet someone's already got that figured out. Is that true?
Is it 63.75 miles?
Oh God, are you serious?
Yeah.
Oh my God. Well, I guess that makes sense because there's like a symmetry here, right? Like it was 70 there. Okay, yeah. Still, kind of cool. Amazing. Is that the true distance I traveled?
Probably not.
Probably not, right? Because when you're driving in a car, you're not going 50 and then suddenly going 75. I don't know what kind of car that is. Because actually your velocity probably went more like this, right? There was some sort of acceleration to there and some sort of deceleration to there. And then here you probably didn't keep a constant speed. And then we went to 70 here, right? So 70. So your velocity curve probably looked crazy like that. Because you're not even ease steady on the pedal. You constantly fluctuate just a little bit, even if you're keeping it semi-constant. So our problem is, if that's my velocity curve, how the hell can I actually figure out how far I've traveled? And the gain comes down to the way we started. So let's actually go to that. Let's say my velocity curve looks like this. So here's my velocity at time t, here's t, and we'll still start at 85. It don't matter, because I'm just going to draw an abstract picture here anyway. But my velocity, I'm at 85, because all suddenly I'm much faster. See the fuzz, start decelerating. Police gone, and I come up, and then I just got some weird shit like this. So this is my velocity. How do I figure out how far I went? And here's the game. I'm going to cut this up into little rectangles because I can find how far I've traveled if my distance is represented by a rectangle. It's just the height, my speed, times the length of time I was going that speed. So the plan here is, and I'm going to make this a little sloppy, I'm not going to write it up, and it'll be on video, but I'm going to cut this time up into parts. I'm going to pick a representative velocity in each of these time intervals. So here, let's go with the right end point. So I'm going to say, oh, for that whole time I was going that fast. And I'm going to use that. God, I'm having trouble with straight lines today. So there is the rough distance I traveled. The velocity I was here times that delta t. So let's actually start getting some differences here. So delta t is just the time difference. And I'm going to just cut these up, and you can make these equal or not, but I'm going to go to the right end of each one of these, cut them up, and get this estimate. And this was what the Babylonians were doing. This stuff right here. Check out how some of these are clearly underestimates of the velocity. This one's an overestimate. This one's going to be an overestimate. But it's a way to do it, right? I've got some raw data, and I want to make an estimate. And then this last one, boy, that's pretty weird. Like that. So if I add up all of these rectangles, so add up the area of these rectangles, to get an estimate of the distance traveled. And I should be a little clear here. Probably I want to say total displacement, to be really precise. This process right here is a step toward integration. So this is like the most primal level of it. This is probably what you'd have to do. You're a scientist. You're a scientist. You're all scientists. You're all going to be scientists one day. You're a scientist now. You're studying the world. You're investigating the world. Scientists don't get graphs of phenomena. You don't study a population and get some beautiful y equals f of x chart, right? Like you don't get a function that represents the things you're studying. What you get is a data table. Science is all about tables, right? So you have time, and then you have the measurement. And this is in discrete, like 0.1. Don't write this down because it's not going to go anywhere that's worth writing down. But you've got some measurement here. You might have 1,000 pieces of data, but in the end, as a scientist, all you've got are discrete points of data. And so if you were doing any work, if this represented velocity here, the only thing you could do as a scientist is what we just did there. But we're not scientists in this class. You're going to take on the hat of a mathematician. And one of the reasons I like math is because it doesn't have to model the world. I used to be a very mystical young man when I was in college. I didn't like science because I was like, oh, science, trying to say something about the world. How do they know what the world is? Maybe you felt this way too, some of you. Just like, don't tell me what the world is. The world is something much more mystical than you could ever have in a beaker, or on a computer. I've changed my mind a lot on that. But in some ways, I still hold that view. And so that's why I'm a mathematician, because math is mystical. And then you get to write mystical formulas, right? Write beautiful things like that, and it looks like magical writing. I wanted to be a wizard one day. I'll just be straight with you. I thought I was a wizard. At one point. Not like fake. I thought I was like a real freaking wizard. Okay, so anyway, enough of that. I hope you'll be back on Wednesday. So integration. Here let me lay out the formal process here. The formal process. This is going to get very mathy very suddenly. So I've got x-axis, and here I've got a function that I want to graph, y equals f of x. You will find that every arbitrary function I draw looks exactly like that. Who knows? Who cares what it is? That's not the point of this. The point of this is to explain what an integral is, a definite integral, what that is. So the problem here, and this is a good one to do. Problem is find the area A, this thing right here. And then again, I know this bounding curve, it's y equals f of x. I want that area. I want the precise area. If that was a square, I'd be home free. If that was a trapezoid, I'd be home free, because trapezoid formula is well known. Take the average of the two heights times the base, you got your area, your trapezoid. That's solid, but I got a freaking curve. So what I'm going to do is cut the interval A to B into n pieces. And if you ever have trouble deciphering what I've written, please let me know. Please shout out. So over here, and I'll always come back to this little picture here and do that. So I'm going to cut this into n pieces. They don't all even have to be the same. I'm going to emphasize that. I'm going to put a little dot, dot, dot here, because I don't quite know how many pieces. So n could be 10, n could be 1,000. I don't know what n is. So I'm putting these little dots here to show, more hash marks, but I don't know how many. There's n of these, so let's see. So this is 1, 2, 3, 4, 5. So let me actually label these a little bit here too. We know that this is A, that's x equals A, that's x equals B. This is my first hash mark, second, third, fourth, fifth, sixth. And then I don't know what happens. This would be my, let's see, so if we were cutting this into n pieces, notice that this is one piece, that's two pieces. So if there's one here, there's one piece to the left. If it's two here, there's two to the left. So since there's n pieces inside this whole thing, this must be numbered n. And the one right before it, what would it be numbered?
1.
N minus 1, beautiful, thank you. So if this was 1,000, this would be 999, right here. So that's step 1, cut them into n pieces, don't all have to be equal. This is called a partition. So I'm going to partition this closed interval. Step 2. In each of the resulting subintervals, subintervals. How many of those are there? How many of these little, this is like a subinterval. How many of those do I have? N. I have n of them, right? Because the right n number tells me how many subintervals come before it. So if this is n down here, there's n subintervals. And so let's actually insert that. The n subintervals there. Choose a representative. And we're going to call it x star sub I. And this little I tells me the subinterval it's in. So this is equal to the rep for the ith subinterval. If at any point along the way, like I really want you to understand this, and I know it's probably like, oh my God, it's like it just starts sounding like blah 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 blah. Really try here, really focus, because this process is going to come up over and over again, and I want you to get it. And you don't have to get it today, but I want you to like clear up any things you're like, what? Are we good? Is there anything I can clear up at this point? Take that as a no, or I don't even know if I know that answer. And that's okay. So what I'm going to do is over here, I'm going to pick in each one of these. So in this first subinterval, I'm going to pick any point inside there, and that's going to be x1 star. And then the next one, I can pick another point. Notice how it's like they're not in the same place. That's x2 star. And then here I'm going to pick x3 star. I'm going to do that all the way across. So in each one of these little spaces, these little intervals, I'm going to pick a point, and that's going to represent the whole interval. That's what I mean by that. I'm going to use that to determine the height of my rectangle. So what I'm going to do next is say, okay, above x1 star, how high is the function? Go up there and make a rectangle that high with the base width of that little subinterval. That's this next step. Above each subinterval, make a rectangle of height f, the function, the top function, f at that point. So this is for the ith interval right here. If this was an x sub 1 star, that would be the height of the first. If this was a 10 here, that'd be the height of the 10th rectangle. So above each subinterval, make a rectangle of height, blah, blah, blah. Okay, so we're going to do that. So I come to this one, and that's going to be that high. In the example we did earlier with the velocity and distance, we were using the left and right points in turn as the heights. And then come out to this last one. Let's see, let's pick on, boy, that is, woo! Oh, Lord. Fix that to be a little straighter. Come on up here, top that off. There we go. And then there's a bunch more inside here. So we're making a bunch of rectangles. In the end, this picture's gonna look like this. I'm gonna draw a little version of this picture right here. So that was my original thing. That's A, that's B. And what I've done right now is I've actually turned this thing into a collection of rectangles. So that's where we're at right now, just a bunch of rectangles. I can find the area of each of those. It's so easy. It's just the base times the height, and I've got all that information available to me. And I'm just gonna multiply, get those areas, add them up, and I've got my approximate area. So, step 4 is assume that delta x sub I, so delta, capital delta, in math and science equals change. You've probably seen that. Lowercase delta is a whole other beast. But that capital delta represents change. So this is equal to the width of the ith interval. And I know what gets weird in this, just hearing ith and nth, and oh my God. I know that when you're not used to that, it really starts to sound like, you know, the sound of the speaker or the projector at the beginning of class. Width of the interval. Yeah, we'll just leave it at that. Then the area of the ith rectangle. I don't know why that ith got all elevated like that. It's kind of weird. I didn't intend it. Is the base, so this is the base, times its height. And its height is the value of that function at the representative point. So its height is going to be this, f at the representative value for the ith interval. So like this guy right here, if this is x sub I star, actually, here, no, let's just draw a separate picture for this. That'd be nice. So this is delta x sub I, and then this height here, that's our representative point, is f at x sub I star. And so this is your base, and this is your height. And so we're just gonna multiply, get those, we're gonna add that shit up, and we're almost done. We're almost done, friends. Hang in there. Hang in, almost done. Today is probably the heaviest day of the whole semester because this. Step 5, add up all the areas. And so that's gonna look like this. The height of the first one is x1 star, f at x1 star, delta x1, f at x2 star, delta x2, and then I'm gonna put dot, 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 because I go all the way out to the last one. And put a plus in front of that guy. And now I have the approximate area. So right now, this is an approximate area. I could use this. If I had a data set and I was a scientist, I'd be done. We're mathematicians for this semester, so we're not done because we like infinity. That's one of our friends in this class is infinity, and we'll talk about infinity a little later, special event, special module. I want to show you some notation here. So, using sigma notation, and sometimes that's just called summation notation for that nice alliterative effect. This is equal to, so first I put a capital sigma. That's capital sigma. People's sigmas get really weird. it's okay. It looks kind of like a sideways M, right? So that's capital sigma. This is a lowercase sigma. That's like a statistical thing for standard deviation. This is our friend. And I'm going to put the arbitrary term here. So this is the area of the ith rectangle. And I'm going to add those all up. And I just tells me which rectangle I'm at. And so I starts at the first rectangle and ends at the last rectangle. I goes from 1. So when I write this, what this means is this up here. This means I goes from 1, 2, 3, on up to n. And I add up all those results. Add up. It means that. All right, almost done. This is approximate. All this, everything up here is approximate to get the true area. The truest area where there are no more rectangles. What we're going to do is what? Any ideas? How many rectangles do I need? Infinitely many. Do you see that the more rectangles, and I really want you to try to see that the more rectangles we have, the better this approximation will be. The better it will fit that curve at the top. So the more rectangles, the better. We're mathematicians. What's the most? Infinity. So what we're going to do is let the number of rectangles go to infinity. Another way to say that is to let the base of the rectangle shrink to 0. Now this sounds weird, but it works. To get the true area, and I'm going to put here, you get an option. You get to choose what you want. Either let n go to infinity, the number of rectangles, or let delta x go to 0 in each subinterval. Either way, when you do that, let's call this star. So star becomes a number. And on Wednesday, I'll get an app out that I don't have it ready yet, but I'll show you this with an applet on the web. Becomes a number, i.e., the limit. Here's some fun. This is the kind of shit you take a math class for, because you can write crazy looking things and impress your friends and family. Say, that's what I did in calc today. The limit of that sum, if it exists, is a number, and that number is represented by this symbol collection. And then calculus begins, finally. So just keep in mind, this is a number. And what it represents for us is the area, the precise area under that curve between x equals a and x equals b. This is called the definite integral of f of x from a to b. Yay! Voices. After long breaks, my voice needs to get back up to speed. I can feel it dying, but I'm not going to let you out because my voice is dying. You're still here for a little bit more. God help us if we had to do that. If we had to go through that every time we wanted the area under a curve, holy shit, nobody would do anything. Nothing would get done. So, how do we do this with less pay. We use the fundamental theorem of calculus, part 1 or 2, it depends on what book you use. We use 1/2 of the fundamental theorem of calculus. We use, I'll just say, part 1 of the fundamental theorem of calculus. FTC, if you just, if I ever say FTC, that's what I mean. What does that mean? That thing down there, which says, this whole process which is represented by this. So like when you see this, and you will see this a lot. Now you're gonna be sleeping seeing this, I'm sorry to tell you. Because you're gonna be seeing this all day. When you see this, it means that. What we just did, it means the last half hour of class. Okay? This is a story right here. This is history right here. This is all sorts of things. This is infinity encapsulated right here. Good news, you don't have to think about any of that shit. You can just find the difference between two things. What's that capital F? Where big F is any antiderivative of little f. Now we're gonna start doing calculus. Now you're gonna feel it's gonna get a lot better. I promise. I mean, and everything's relative. Keep that in mind. So all my promises hinge off whatever that previous experience was like. So let's do this. Example. Find the area under y equals x squared between x equals 0 and x equals 1. I like pictures. Y equals x squared. Parabola. I don't like that parabola. Like that. And then here's one right here. I want this. I want that beautiful area right there. So I set up the integral. Oh, yes.
I'm not sure if I'm, so you just find the antiderivative and then you just subtract it and that's it there?
You plug in the end points and then subtract.
Okay.
Yeah, exactly. You're going to see that happen right now. So yeah, great question. So first off, this area, let's call it A. A can be represented by this symbols, these symbols. Bless you. Bless you. So I would read this as the integral of x squared from 0 to 1. I'll write that out. Fundamental theorem of calculus says I need to find an antiderivative of x squared. And yeah,
1/2 x cubed?
really freaking close. The 1/2 is off. 1/3. Yeah. So okay, all right. So our friends here are using what's called the power rule. Let's talk about that. So we need some rules. For God's sake, we need. We don't need need. We have plenty of need. We need some rules. Well, let's put a couple that you probably talked about at the end of the semester. So here's f of x, and here's its antiderivative, an antiderivative. So this is antiderivative. So if you have a power of x, the way to take the antiderivative is to increase the exponent by 1 and divide by the new exponent. So watch this. I add 1 to the exponent, and I divide by the new exponent. And if you think of it that way, first increase the exponent. So like you do a good job on the x cubed. Just use that new exponent and put 1 over that in front, and you got it. This is good. Ooh, what would be bad for n here? What would be a bad n? You don't want to divide by 0, so what's a bad n?
-1.
Negative 1, right? So this is good if n is not equal to -1. In other words, this thing isn't 1 over x. So if I have 1 over x, which is x to the negative first, can anybody know what the antiderivative is? Whose derivative looked like this in Calc 1? Oh yeah, hell yeah. And we pop these absolute values on for good measure. Let's get a couple more up here while we're here. What's the antiderivative of e to the x?
Just e to the x.
Hell yeah. That's like one of the greatest things in all of calculus, right? E to the x, its derivative is e to the x. Its antiderivative is e to the x. That shit is gold. That's easy to remember. Let's just do a couple more just to see where we're at. I know we're good on time. What about cosine? Antiderivative of cosine. Whose derivative is cosine? Just a good old sine. Good old sine. Sine squared gets a little crazier. Whose derivative? This one's a little trickier. Whose derivative is sine?
Negative
Oh, well, damn. Yes. Beautiful. You can get really far. You can get really far with this. You'll get quite far on your homework, on web work, with just this little list right here. I don't think there's anything else. So we've got our list here, and now we can do this. So this thing here, I take the antiderivative. Oop, wow. Increment the exponent by 1, take the reciprocal of that new exponent out in front, and check out this notation. This means evaluate at 0 and 1 and subtract. So this is like a precursor notation. And I'm going to ask you to use this to keep your head straight. If you've had a math class with me before, you've heard me say many times, especially if you're a person who didn't like to write stuff down, and he knows who he is, that math notation is technology. It helps your brain. Like literally writing this stuff down, you don't have to carry it anymore, right? Don't you wish you could do that with all the other shit you carry through this life? All the burdens and guilts and pains and sorrows. I wish I could write them down and not have to carry them anymore. I guess that's what a journal's for. So this is like a math journal. Lay it down on the page. It's gone. So this means I'm going to plug in the top limit. So plug in the top, subtract, plug in the bottom. And when I say plug in, I mean into this formula here. And then do that shit, right? So that's just the third. 1/3 unit cubed, whatever our unit, squared, whatever our units were. I think it's kind of cool that the area under that parabola is a third. Perfect third. So beautiful. Right? There's something really beautiful about that. What's the area of a triangle? Like if I had a triangle across here, imagine this was a perfect triangle. What would be the area of that triangle?
1/2 base times height.
Yeah, 1/2 base times height, so the area of that triangle would be a half. This is a third, so this is actually a little bit of a sixth. Right inside there. Sorry, I'm just riffing now. It's having some fun. It's like entertaining myself with things I'm saying. Let's practice. Yeah, we got a good 10 minutes to get warmed up on this. So this whole thing, this thing here is called the definite integral. there's an indefinite integral, and we'll spend more time with that on Wednesday. Don't worry, it's nothing new. You don't have to go through all the pain that you already went through. But could you please find this one for me? Let's start off chill. One, two, x to the fourth. I'll draw the picture. We're going to find the area here. Your y equals x to the fourth. This is what you come to math class for. Getting to do soothing problems. Problems that we can solve. Jeremy, sorry, that's right, sorry.
And I'm trying, I just haven't got my notebook.
Oh no, my friend, oh that sucks, you should have let me know it earlier. I was like, damn.
I just don't have any paper.
Oh, that's so sad, that's terrible, never go without here. Here you are, yeah. And you can see all the notes if you need to like write them
I
down.
think that's how you did
I didn't mean to embarrass you.
it.
I was like, man, is he doing this in his head?
I think I almost had it.
That's
It's
cool.
part of the fun of Calc 1.
Doing it in your head,
Yeah.
writing as little as humanly possible, yes. What's the antiderivative?
X to the fifth over five.
Yeah, x to the fifth over 5. I like to do these as fractions out in front. You can put it over 5, totally cool, not a problem. And we're going to evaluate that from 1 to 2. Plug in the 2. Plug in the 1. Subtract. 2 to the 5th is 32. 1 to the 5th is 1. The kind of thing you don't guess, right? You don't guess that area. Nobody guesses 31 for anything. All right, let's do another. Any questions?
What would the units be on that one?
I'm sorry, say that again.
What would the units be on?
Ooh, let's make up some units. Somebody give me a fun unit of length. Cubits? Cubits. Sorry. Yeah. So yeah, our units are cubits. Cubit squared. I don't even freaking know what a cubit is. It's like something Noah used or something, right? Like, or so the legend goes. So, any other questions? I like that question because we're doing area, right? So it's kind of like nice to actually have. Are you a physicist? You gonna be a physicist?
No, I'm going to computer science.
You're going into computer science. You feel like a physicist with that question. That's good. I like it.
I'll take that.
Okay, new one. That's a 1. That's a square root. Little move you have to make here first, right? Convert that into a power. What power is that? 1/2, yeah. So when you see this, your first step is that. And that's kind of why I like my little reciprocal game, because taking the reciprocal of a fraction is just flipping it. This is probably our last problem for the day. You've done a lot. Exponent, bump it up by 1. So 1/2 plus 1, what's that?
3/2.
3/2, beautiful. 3/2, sorry, I'll get down so block your view over there, sir. And so that's that, from 0 to 1. Oh, reciprocal out front. Lots of people do this. I've seen students write this and carry that shit with them to the end of the problem. Let's minimize our burden and our loads. All right, to take the reciprocal of a fraction, you just flip it. It's all good. So then plug in our limits. One to any power? 1. 0 to any power? 0. Except for 0, right? Oh boy, that's a whole, that's a ball of wax. We'll do that later. We'll talk about that some other day. So this is 2/3. Done. That's the area under here. I just want to point out a couple of things. So the area under here is 2/3 meters squared. Sure. We'll like go a little modern here. Move out of like whatever the hell that was. Long time ago. So the area under this is 2/3. Notice that this, if you know about inverse functions, that's the inverse of x squared. And the area under that little bit was what? 1/3. What's the area of that full square? This square here? 1 whole. So notice how this piece here is the same area as that up there. That's actually a little hidden square root kind of area up inside there. It's kind of cool. It's, you know, you find it cool, you know, it's okay. It's all good. You can handle it. I'm tough. All right, friends. Thank you. Woo. All right, so what's homework 0?
Go log in.
Do something.
Log in, just do something. The most general thing is log into freaking Weber. Email me if you have any trouble ASAP.
Oh my god,
Right
I'm
after?
so excited. I'm excited.
So it's they're like, hey, we should do I'm just taking photos.
Oh, okay. That's standard. Yeah. I take it.
I'll try to put tough as soon as I can, and not change things in English, and I'll just give you what I have, and let you know speak this good. Is that okay?
That's great. And with all I ask is I'll probably lose that.
Okay.
I'll just give me a heads up. And we'll work everything out. I got you covered.
Awesome.
Okay, awesome.
What
Thank
lab
you.
do you have?
Hey, John.
Thursday.
Felt like I have to introduce myself again. 'cause
It's been a long time.
You have to do
Have you
that
gotten
every
taller?
class.
What was the history?
You look good.
I don't have an
You look
understudy
good,
yet, but I
my
think it's like survey,
Last
Latin
semester I was
American or
trying
something.
to say
It's one of my RCC like.
every class.
Yeah, I noticed that because like we weren't coming. Excuse me, would you hit stop, please?
Yes.
Thank you so